Hello, welcome back to the channel. So let's do one more question on using substitution and evaluating a definite or an indefinite integral. So in this question, as it is explicitly mentioned that you have to use substitution in order to evaluate this definite integral. And the way we approach substitution is we first identify the function and see if the derivative of that function is also present in that expression. And as we also discussed in the last video, what we do in substitution is, in our integral expression, we identify a function for which we also have a derivative of that function in that integral expression. And if we have those two components, we proceed on using substitution and solving a definite integral or an indefinite integral. But the catch about definite integral is that whenever you are using substitution in definite integrals, you also have to take care of your endpoints. So before solving this question, let's first look at this integral expression and see what function do we have for which we also have a derivative to that function attached in our integral expression. So let's start with this cos expression. We know that if we differentiate cos, we would get minus sign, but we don't have any sign component in our definite integral. Now let's consider this function e to the power x square, and you know that when you have a function, for example u equals, let's suppose our function is u, and let's suppose it's e to the power x square, and when you'll differentiate this function with respect to x, what would be the differentiation of that? So we'll use chain rule in order to do that. So it would be e to the power x square, because the derivative of e to the power something is e to the power something, and then because of the chain rule, we'll also have to take the derivative of x square, right? That is done because of the chain rule. And since we know the derivative of x square, which is 2x, e to the power x square would remain same and it would be multiplied with 2x. So the final expression in this case would become 2x e to the power x square, right? And you see this thing, we have an x e to the power x square in the derivative expression, and we also have x e to the power x square in our original integral expression. So that gives us a confirmation that we can definitely assume our u to be this function, so that we have a derivative to this function also present in our integral expression. So let's further simplify this expression down. So this is du by dx. As you know, if we shift dx to the other side, it would be du equals 2x e to the power x square dx. And since we only have x e to the power x square and dx, let's shift the 2 over to this side. So that would be du by 2 equals x e to the power x square dx. So now I have this component ready. So what I can do is, instead of now, since I've assumed that my e to the power x square is u, I can substitute e to the power x square in this expression to just u, and instead of x e to the power x square dx, I can just simply use du by 2. So let's do all those changes, but before we do all those changes, we also have to care about the endpoints, because now instead of dx we are using du, so the endpoint should be based on the function u rather than based on x values, right? So that is why let's divide the segment. So we know that our lower endpoint is x equals 0 and the upper endpoint is x equals 1, as you can see, right? Lower endpoint is x equals 0, upper endpoint is x equals 1. Now when our x is equal to 0, which is the lower endpoint, our u is equal to e to the power x square, which is e to the power 0 square. This is e to the power 0, which would be 1. So when our x is equal to 0, our u is equal to 1. And similarly, when our x is equal to 1, our u is equal to e to the power x square, which is e to the power 1 square, and that is e. So when we'll do the substitution of x and change everything to u, the lower endpoint, as we can see, will be changed to u equals 1, and the upper endpoint will be changed to u equals e. So let's do all those changes and now calculate the definite integral by doing substitution. So let's first write the original expression, which is integral 0 to 1 x e to the power x square cos of e to the power x square dx. And if we further simplify this down according to the substitution values, let's rearrange this equation so that we can clearly visualize the substitution. So I'll take cos first. This would be cos e to the power x square, and the rest term is x e to the power x square dx. And as you can clearly see, x e to the power x square dx can be changed to du by 2. This would become du by 2, and e to the power x square can be changed to u. So this segment can be changed to u. So now the final expression after making all those changes would be cos of u, and x e to the power x square dx would be changed to du. But now our endpoints cannot be x equals 0 to x equals 1 because dx has been changed to du. So that is why we will use the new endpoints that we calculated, which is starting from u equals 1 and ending with u equals e. So u equals 1 to e cos of u du, and we already know the integral for cos, which is sine. So this integral will be equal to sine of e minus sine of 1, and that would be, and you can just leave this answer as it is, and which would be your final answer. So that is how we use substitution in order to evaluate our definite integrals. So there are two important points that you have to keep in mind. You have to first identify the function for which you already have a derivative of that function attached in your integral expression. And the second thing is, whenever you are calculating a definite integral by using substitution, you have to make sure that your endpoints are changed accordingly to the function transformation. So these are the two important points that you should consider when solving definite integrals using substitution. So that's it for this video. Feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.